simulation, also to train deep network kind of architectures. I'm sure many of you have seen these interactive 3D environments that especially I think the computer vision and also the NLP community have come up with, where you have somewhat photorealistically modeled 3D environments that an agent can move throughout, also with manipulation tasks. And I think there's a lot of really exciting work actually going on in that community, and where people have shown that they can learn actually very good policies, low-level navigation policies, or even higher-level visual reasoning policies that have a very good chance of transferring to the real world. The robotics community, which is, I guess, us, has been, I think, very slow actually at embracing these kind of environments, right? And the reasoning is exactly this, like John Leonard always, I think he cites Hugh Durant-White for having said that, and Rod Brooks about simulation is doomed to succeed. So there's this notion in robotics that if you do things like mostly in simulation, then you're just going to overfit to your simulation capabilities and it's never going to work in the real world. I think a more modern take on that is just this notion that the sim to real gap is too large, right? Like if you train something in simulation, also the transfer to the real world is not going to work. And therefore we should do, I don't know, maybe 90% of our work in the real world so that we're sure it's always grounded in the real world. However, I think even in these environments, people have shown that navigation capabilities actually transfer.
Where are you coming?
Visual navigation capabilities. And one thing that coming from a manipulation perspective is that they have a pretty high level of abstraction, especially when it comes to manipulation, right? So sometimes the agent just has to have looking at a scene and then be able to, for example, segment out an object, and then you say pick up, and whoop, it's in the virtual gripper of the robot, right? So of course, as robots, we say that's not going to work, right? So we need to get robots to actually execute these kind of tasks in the real world. And I just want to that we are getting actually pretty close to being able to execute many of these, at least pick and place tasks in the real world. Okay, so the first part, I'm going to talk about some actually early work we did on learning to grasp unknown objects, where the goal was, if a robot doesn't have a model of an object, how can we train, for example, deep networks to enable robots to pick up objects that it hasn't seen before. And again, I'll highlight things where we actually really leverage simulation. And one way to train a robot to grasp unknown objects is you, for example, if you have a 3D model of an object, this is the red is a shape model of the famous, what's a tuna can? Oh no, the potted meat can, I think, where you have like your 3D shape model. And then what you can do is you just randomly sample many thousands of possible ways the gripper could try to pick up this object. And then you feed that into a physics simulator. And then doing the physics simulation kind of tells you which of these grasps actually succeed at picking up this object or not, right? You just shake it, do things, and if after shaking it's still in the gripper, then you know that was a good grasp. Now what you can do with this is, you can do this for actually many objects. So we did it for the ShapeNet data set where we had almost 9,000 objects. And for each object, we did these kind of simulation runs that you can see on the left. And then for every object, you see this on the right, we get these green lines that indicate good gripper poses, which means these are poses that worked in simulation and had a high chance of succeeding. And again, you do this for a good number of these objects. And now at least we have a data set that we can use to train, hopefully, deep networks in order to kind of replicate that behavior, not assuming that you have a 3D model, but based on point cloud data, for example. Okay, so here's how we did this. There's 2 lines of work where we did this, the 6D grasp network led by Arsalan, and then Martin Sundermeyer in intern did contact grasp net. But the high-level gist of how we use the learning is very similar. So what we can do then, if we have this data set, we can, for example, just simulate a point cloud, a depth camera observation onto an object. And then we can train, in this case, it's called a conditional variation autoencoder. It's a reasonably standard technique these days. we can then train this network such that it takes as input the point cloud and it samples 60 graphs according to the distribution that came from the training data. And since our distribution focused on graphs that are successful, it is trained to generate graphs that have a high chance of succeeding on the object that is represented by this point cloud. We can now even refine this by adding another network to this, which is called a grasp evaluator, that takes in a point cloud of the object along with the gripper that was, for example, sampled by our first network. And that network is just trained to evaluate what the chance of success is. So it's kind of has a more refined understanding of the success. And thereby we can, for example, rank sampled graphs by their quality. Since it's a deep network, we can differentiate from this, and we can even use this network to refine the graphs, which means we can change the pose of the gripper such that the probability of success of the grasp is increased. Okay, so we can now do this for unknown objects. And again, once this is trained, all you have to do is you feed in the point cloud of an object. The first network suggests grasps. The second network refines them, and then you choose one, for example, based on which one is more convenient to pick up and things like that. This actually worked more or less out of the box without any real-world additional training data. So these are objects, you know, some of them the YCB objects. In this case, they're just standing on the table, but we had a very good success rate, solidly trained in simulation, and then just depth camera data. And we all know depth camera data translates reasonably well from simulation to the real world. This example here just shows, and also important, sorry, these objects were not in the training data, right? So the object models were not in the training data, and it was all in simulation. Now, if you want to go to more interesting scenes, maybe cluttered scenes, and want to pick up a specific object, then you also have to reason maybe more about segmentation. So I just want to give you one example of some work that we've done in the direction it's called unknown object instance segmentation. So the vision community has focused a lot on work that is kind of like mask RCNN, where it's about segmenting objects of certain categories. But in robotics, often we have to deal with objects from categories that you just haven't seen before. So here we just want to see, kind of have a measure of objectness, right? You have a scene. You don't even reason about what types of objects these are. You just want to segment it into individual objects. And this is work that was led by Yu Jiang, who is actually in the audience now, faculty at UT Dallas, where the input is, for example, an RGBD view of the scene. And then he feeds it through a fully convolutional neural network. And the output is a dense feature map, which assigns each pixel to a feature space such that pixels that are on the same objects are very similar, and pixels that belong to other objects are dissimilar. And this is what's called, I'm sure many of you have heard, contrastive learning, contrastive training. And we can train that network then again, just on simulated data, right? Synthetic data set where we just randomly sample objects, sample poses with the occlusions, and we can, of course, automatically use these instance labels that you get on the right. We can use these to supervise the networks to give this, to supervise the similarity measure that the network then has to learn. And it turns out, again, this transfers actually surprisingly well to the real world. So here's an example. Here's some input images of cluttered kind of tabletop scenes. This now shows the feature projection, color projection of the feature space that the network assigns to that scene. And then we're applying 2 stages of mean shift algorithm for the clustering. And the output then is actually what you can see here on the bottom. And it's never, of course, absolutely perfect, but I think this is already something that is certainly good enough to be extremely useful for manipulation tasks. Now, once you can do this kind of segmentation, we can now combine it with the ideas for the grasping and come up with a system that enables us to grasp. There's also, of course, here some highlights on how the segmentation improves with this 2-stage process. But here's one quick example. It also actually coincidentally works reasonably well for transparent objects. As you can see here, we didn't specifically train on those, but you can, if that's an important task, then you can, of course, you incorporate that into your training data as well. So now we can start at least thinking about more cluttered scene. How can we do 60 grasping, but with unknown object models again. So here's the idea. You have input is observation of the scene. We can segment it, as I just hopefully convinced you of. And now imagine someone says, this object number 3, we don't care about what type of object it is. The robot should pick that up or should get this out of the scene. What we can do is we can kind of cut out a local scene around, for example, this case, the mustard bottle. We can feed this into the GraphNet that we trained on these many objects. And then we can actually, also what we need to do in cluttered scenes is we need to reason about occlusions and context with other objects in the scene. So it might be, for example, that none of the grasps that you need to execute in order to pick up the object is actually accessible because there are other objects around it and you can't actually reach those. Okay, so for that you need to occlusion checking, and it turns out if you do occlusion checking simply on the point cloud, that you are missing out on many collisions because parts of the objects are occluded, right? You have a viewpoint onto the object, you don't see the backside. So if you do collision checks only on the point cloud, you're going to miss out on those collisions. And in order to overcome that, we developed something called collision net, where you can actually train a deep network that takes in a point cloud and it can do the collision checking for you. And because it's a deep network, we can parallelize that, and it's actually also extremely fast. Okay, so now what you can do with this then is kind of one step further, where imagine, so here's the scene, here are the objects. On the right side, you see actually the view that the robot is using to do the reasoning. Left is just kind of giving you an overview. So imagine the user says the robot should pick up that white mug coming from the automatic segmentation. And then now in this case, the scene collision net figured out that none of the grasps were actually accessible for the white mug. And it can determine for the other objects which of those contributed mostly to the collisions. And in this case, it's the one in red. It has the highest probability of being in collision. And we can now just go back and say, well, obviously, I got to get that object out of the way. So now we just revert to changing the task to saying, okay, this is now our target object. We do the grasp generation. In this case, the robot determined there are actually grasps that are accessible. And the robot can now just pick it up and move it out of the way. Again, importantly, there's at no point to reason about object types or something like that in this case, right? It's really all just based on a point cloud. So now it goes back to the original scene. In this case, it found actually a valid grasp for the coffee mug, and it can now finally retrieve the coffee mug. Okay, so this is just to give you an example for how we can use these simulation capabilities and that they transfer actually very well to the real world. We've done also a lot of work on kind of semantic placement and things like that, but I just don't have time to go into all these details here. So rather than expanding more on that, I want to give you one more example. That's some very recent work. That's an upcoming RSS paper led by Yashna Rang, which is on context-rich tasks. So far, the tasks that we've seen for manipulation, it's kind of still not trivial, but reasonably simple, right? Also from a simulation perspective, actually. It turns out it gets much harder if you want to simulate tasks like industrial tasks, like very tight insertion tasks or screwing a nut onto a bolt and things like that. And for these industrial kind of tasks, actually NIST, they developed a benchmark board, which is a real hardware thing that you can actually acquire from them. And then you can do your experiments on these. And there's some, for example, really nice work that's been going on, Stefan Charles' lab at Intrinsic on how to use reinforcement learning in this setting. And I always wondered, like, why there's no simulation versions for these kind of tasks. And it turns out it's really just because simulating these very tight contact environments turns out to be very, very difficult still. So we've all seen, as you see, for example, on the left, like the work done by OpenAI, also NVIDIA, and if you see Marco Hutter's talk, we've seen a lot of success on actually training agents with these kind of tasks that require a lot of reasoning about contacts with the environments. And these models actually transfer surprisingly well often. But again, if you go to the simple task of threading a nut onto a bolt, I was very surprised. It turns out to be very difficult. So if you look on the right, this is, for example, from some work in 2018, where they tried to simulate that with using PyBullet. And just as a caveat, the screw kind of that is simulated here is much larger than a real kind of metal screw you would see. So it's actually supposed to be much easier. But then often what can happen is that your simulator is actually not stable, right? You're getting this wiggly behavior, and it might even do crazy things. And here's some more recent work where they actually then managed to get this behavior, to model this behavior actually very well, right? And again, you need very fine-grained models for the surfaces to reason about the context and the forces and the frictions and all of that. But if you look down there, first of all, again, this is not a real scale nut-bolt interaction, and it's 1/350th real time, which means it takes to simulate, it takes 350 times as long as just if you would have done it in the real world. And then sometimes we might say, well, that kind of beats the purpose of doing it in simulation. So we've been working, and Yash especially has been working with the simulation experts at NVIDIA who are doing all the physics simulation. And you know, Flex and Miles Macklin, for example, has been a great collaborator on that, on seeing how we can speed this up and still make it work well. I just give you the gist on the left. So the idea is that, for example, in this context for this nut and bolt interaction, we actually, how you represent these objects is very important. Typical representation is like these mesh representations. It turns out that reasoning about the context between the nut and the bolt using just meshes is very slow, takes a lot of time. So what we do instead is the bolt is represented by a signed distance function, a signed distance field, which we as roboticists, of course, know very well. And of course, graphics simulation community has been doing this for a long time. And then it turns out that you can actually, so the nut is represented by a mesh. And using this representation, you can actually very quickly compute these contacts between the nut and the bolt. And as you can see here in the middle, these are kind of, each line represents one contact and the normal of the contact surface. And we can compute these 16,000 contacts in this case, for example, in less than a millisecond on a GPU. So that's already pretty nice and fast. It turns out that that is still actually too slow if you now want to resolve the physics of these interactions, like all the forces that you need to compute. So the next step is we are reducing actually these contacts to just, in this case, 300 by doing some clustering on them, and also based on the surface normals and things like that. And if you do all of these tricks and put them together and know how to implement all of that very well, then we get actually to this system where now we can, again, beforehand, kind of state of the art was 350 times real time, and we can now do real time, but we can do it with 1,000 of them in parallel on a GPU. Okay, and these are real industrial grade kind of models, right? So this is not like toy size or something like that. So this is the real stuff. Okay, we can now, what's interesting, of course, we showed that in this environment, for example, we can start using PPO to train policies. In this case, we actually trained 3 policies and then stitch them together, let's say. This reinforcement learning, it's not sim to real yet, because it, for example, is based on the 60 posts of the nut. But of course, the idea is now that there's more work to be done in order to do this, but at least with the simulation, we're able to do this kind of work. You might ask now how realistic is the simulation really? So the first indication is actually the fact that we can run PPO and train this this policy on it is already a strong indication that the simulator and the simulation behavior is actually very consistent. And another indication we have is from actually prior work. There was a group by Huang and Sun where they actually had people with a tool. They performed some of these kind of tasks like threading a nut onto a bolt, and they had a force torque sensor. And in gray, you see kind of the distribution that they measured with the force torque sensor when a human does it. And in red, you see the forces that our simulator predicts for that. Now you might say the distribution doesn't match perfectly well or something like that, but if you look into simulation, often these things might be easily off by an order of magnitude or two. So the fact that we are kind of here nicely in the middle indicates that this is actually a very good realistic simulation. Okay, and now we've done this for all the assets that are in the NIST board. Okay, so there's now a simulation environment that captures all of these. Like there's these kind of tasks of this gearing, and you can see there's even a spring in some of these to simulate the behavior very well. And the paper at RSS is going to come out also then with these three kind of types of environments, and it's going to be, of course, fully available to everybody. And the idea is that now actually we can enable the community to look at these problems. Okay, just one very quick note on, we also been looking, of course, a lot what is a hot topic these days on deformable object. This was done especially in collaboration with two interns. Isabella Wang, she gave a talk here at an earlier workshop, and Caroline Martel, where we've been looking at these like deformable objects. There's a data set available also for people where we now start reasoning about how do objects deform depending on where you pick them up, what's the stress field over these objects based on gravity. And then we also tested some of these simulations, what you can see in the upper one here, for example, against real objects, and the behavior is actually very similar. And here we did not fine-tune the simulation, we just use off-the-shelf kind of information about the shape and behavior of these objects. On the lower right, you can see also some work on granular media. I think I have like 2 more minutes, 2-3 more minutes, that's right? Okay. Okay, so I think this is also now probably in the exciting directions for more complex objects and the interactions. I want to just spend 1 minute on some project that we're just starting now, where we really want to see, you saw early on these embodied 3D environments, but we would like to see, can we scale robot training using more realistic physics simulation, using these kind of tools that I just described to you, but still doing more complex tasks. So what we are looking at is, for example, imagine if you can programmatically generate thousands of these kind of, let's say, kitchen cabinet style environments. Okay, that's the first thing we're doing. And then imagine that for each of these environments, you can then generate tasks, which means you can populate them with objects, and we can automatically then generate tasks like put all the coffee mugs into the lower shelf in the cabinet or something like that. Okay, so now we have thousands of different environments, and for each of those we can generate an arbitrary number of tasks, and then we're actually feeding this in a task and motion planning system. So Kaylin Garrett is on our team, he's an expert in task and motion planning. This is still ongoing early work, so I'm just kind of giving you a preview of some of the stuff here, and clearly certain things we will try to make the motion smoother. And in this case, you see on the lower right that the gripper is actually not fully interacting with the bowl. So the idea is we're using this task and motion planning system to generate solutions to the tasks. Then we're going to run this through the full physics simulation that we have. And the idea then is, hopefully, imagine if you have 1 million examples of such tasks being executed in physics simulation, along with the visual rendering, and if you want the forces and everything, that then we can hopefully go to train really large scale, for example, deep network to solve some of these sub-problems and see how all of this will scale, right? Because we've seen over and over again, if you can generate really large data sets, deep learning provides you with very powerful solutions. And at least this gives us now a handle at actually looking at this from a more clear way using these simulated environments. So with that, I wanna wrap up. So I think that the kind of simulation tools that we're seeing, they're constantly improving. And I agree, they're never perfectly ready for prime time, but I think we've seen like really good developments where we can now simulate very interesting scenarios at a good physical level, photorealistic. I think there's, and we can discuss this later, of course, because there's always controversy around it. I think there's many actually advantages of doing these things in simulation, right? So from a training perspective, of course, you can do large scale, the training is safe, it's much faster, of course, if you can simulate things fast. And also what's really interesting, in simulation, you have access to the ground truth state because you're in the simulator, which means we can solve tasks in simulation that we simply can't solve in the real world yet, like all these task and motion planning systems that I just showed you on the previous slide. So the idea is we can in simulation generate examples for desirable behavior, and then we can train, for example, deep networks to replicate these behaviors and train policies for them. Also, this work on these foundation models, we can again discuss this later more, where we can say, if you have such large data sets, what kind of supervision should you actually use in order to learn very general representations that can be used in many different tasks around manipulation. But of course, open questions, still a lot of work to be done. For example, how do you generate all the assets, the environments and tasks for these kind of things? And then, of course, the sim to real, how you transfer those solutions then to the real world. I'm very hopeful that we can actually do this. And moving forward, of course, more complex objects. And I think overall, we always just have to make sure that with all the work we're doing, even if we're really pushing the simulation side, we just need to make sure that we're always kind of closely watching how this stuff works in the real world, because otherwise there's a risk that we're kind of diverging from the real world and we're just happy that everything works in simulation, but we lose track of how it works in the real world, right? I think that's crucial, but if we do this, I think we have a good chance of making really exciting progress. And with that, I'll thank, of course, the great team and all the collaborators that we have at NVIDIA.